So we're almost ready to see our row reduction algorithm for analyzing matrices, but we're going to need one more little set of definitions first. A pivot position is an entry that corresponds to the leading one in the reduced echelon form of a matrix. So looking at this example, which is already in echelon form, the pivot positions are the four leading entries, the 2, the 1, the 3, and the 1. The pivot columns are the columns that contain the pivot positions, and the pivots are the actual numeric values, 2, 1, 3, and 1. So I've got the process here, and we'll talk through it real quick. Then we'll look at an example, which I think always helps to make these things a little clearer. So first, we're going to start with the leftmost non-zero column, and this is always going to be a pivot column, right, with the pivot at the top. We're going to select a non-zero entry in the column to be the pivot, and if necessary, we're going to switch rows to get it up into the pivot position. Now, thinking back to your algebra and pre-calc classes, this is the step where you always look for somebody whose coefficient was 1, right? Because it was easy to multiply that by whatever you needed to do to wipe out the other instances of that variable without introducing fractions into the process. We're not going to worry about that necessarily here. You really could pick any column. Assume you could pick any value to become the pivot. From a software application development perspective, you're actually going to often do the exact opposite of looking for that 1. You're actually going to look for the value whose absolute value is the greatest. There's some technical reasons behind that's got to do with computer arithmetic and the way computers handle rounding. You're less likely to introduce significant rounding errors if you choose your pivot that way. All right, so step 3, we're going to use row operations to make all values below the pivot 0. Step 4, once we've wiped out everything below the pivot, reduce everything below the pivot to 0. Cover the row with the pivot column and any rows above it. Basically, we're not going to touch anything above a row once we've processed it. Then we're going to go down to the next row, repeat the process again. Keep doing this, right, until there are no remaining non-zero rows. And at that point, you should have the matrix in an echelon form. Our goal is the reduced echelon form. So from here, we're essentially going to do the process in reverse. We're going to go all the way to the rightmost pivot and use that pivot and row operations to, excuse me, I always forget the scale step. First, we're going to scale the pivot to 1, right? Divide through by whatever you need to make that pivot equal to 1. Then we're going to use that value to eliminate all of the entries above the pivot in that column. Okay, a lot going on there, right? Let's take a look at an example and see how this actually works in practice. Okay, so we've got a matrix here, right? And you can think of this as the augmented matrix of a system of linear equations. Although you don't have to make that connection, this process works for any matrix regardless of where it came from. So the first thing I need to do is get a pivot in that first column, right? Because I'm going to be doing this by hand, I would prefer to have that 1 as my pivot. So I'm going to switch the first and second rows, and that's going to give me this matrix. Okay, so now I'm going to use that pivot to eliminate the 2 and the 5. Right, so first, I'm going to multiply all of the values in row 1 by -2, add those to row 2. So if we do that, for example, 1 times -2 is -2. Add that to the 2 and it becomes 0. 0 times -2 is 0, so that doesn't change the 1. 2 times -2 is -4. -1 minus 4, that gives us the -5. And so on throughout the rest of that row. Now I need to eliminate the 5 in the row 3, column 1 position, the one that's under my pivot. To do that, I will multiply row 1 by -5 and add its values to row 3. Right? Doing that gives me this matrix. And now we're done. Right? We have reduced everything below the pivot to 0. So now we move to the next column with a pivot. Right? That would be column 2. I'm going to ignore column 1. Right? We're never going to go up. I'm always going to be going down. So I'm going to use that 1 in the 2, 2 position to eliminate the 2 that's below it. So to do that, I will multiply row 2 by -2 and add those values to the values in row 3. That's going to give me this matrix. Okay. And we're almost there. We're halfway there, right? This is an echelon form of the matrix. Right, so now we're at that last step where we're going to do that scale step that I almost forgot. Right, we don't have to worry about rows 1 and 2 because the pivot values in rows 1 and 2 are already 1. Excellent. Nothing to be done there. We do have to make an adjustment to row 3. Right, I need that 3 in the 3, 3 position to be a 1. So I'm going to divide through by 3. If I do that, rows 1 and 2 stay the same, and row 3 becomes this thing. Okay, looking at row 1, there is nothing above that pivot, right, so we don't have to worry about that row. Looking at row 2, the only value above the pivot in row 2 is already 0, right? Excellent, that's squared away. We do have to do some work with column 3, however. There are some non-zero values above the row 3 pivot in that column. So I'm running out of room a little bit, so I'm not going to put each of those steps here. I'm going to multiply row 3 by 5, add it to row 2. That's going to wipe out the -5. And notice how the zeros in this echelon form are helping us out here. Because those values are all 0, when I start adding back up, it's never going to affect the stuff in those 2 columns that already have the values that I want them to have. Right? So multiply by 5, add up to row 2, multiply by -2, add up to row 1. That'll eliminate the 2 that's above my row 3 pivot. And that gives us this matrix. This is the reduced echelon form of the original augmented matrix. So, and that's it. We're done. All right, once we get into that reduced row echelon form, we're finished. Now remember that our goal here was to come up with a solution to a system of equations, right? But I'm actually going to interpret that a little more broadly than they do in those algebra classes and say what we really want to find is the solution set of the system of equations. Phrasing it this way will let us use our method to come up with solutions both to systems that have a single solution, a single set of points, one for each variable, as well as those whose solutions are bigger than that, right? Sometimes the solution will be all the points on a line. Sometimes it'll be all the points on a plane. Sometimes it'll be some more complicated shape, right? Either way, interpreting it this way is going to let us be very general and come up with a method that will come up with the solution to any consistent system, I should say, of linear equations. So we'll look at how to do this for any reduced echelon matrix. That's going to be our topic in the next lecture.